All right, good morning or afternoon or night, whatever time it is for you guys. We're moving on to our next section after you guys completed those review sections, and we're going to continue talking about integration here. So one strategy that you use when you're trying to find an integral is you want to think what function would have the integrand. So when we talk about the integrand, okay, we're talking about the function that's in between the d of x and the integral symbol. That's referred to as the integrand. So if I'm trying to integrate that, one strategy that I can do is I can think to myself which function or functions would have a derivative that is equal to x squared. So remember our rule on a derivative or on an antiderivative. To find an antiderivative, okay, we add 1 to the exponent and then we divide by that new exponent. So a function that would have x squared as a derivative would be x cubed over 3. Or I could write that as 1/3 x cubed. All right, now, is there another function that would also have x squared as its derivative? And if you think about it, there's lots of them. I could take this function, this antiderivative that I just came up with, and if I add a constant to it, like the number 2, if I did the derivative of that, the 2 is going to disappear because the derivative of a constant is 0. So remember, this comes out front. We subtract 1 from the derivative or from the exponent, and then the derivative of a constant is 0, so we don't write it. So this function would have its derivative would also be x squared. So I could come up with an infinite number of these functions that have the same derivative. So when that's happening, what we do is we express this. If I want to write all of the integrals or all the antiderivatives of x squared, I write it as 1/3 x cubed plus c. That c is known as the constant of integration. And it takes care of the fact that x squared could have potentially a whole bunch of antiderivatives. Now, if you notice that when we graphed or when we look to evaluate x squared, there wasn't a lower bound or an upper bound. There was nothing written here. So when you integrate a function that doesn't have an upper or lower bound, that's called indefinite integration. All right, and that'll have, every time that we do a indefinite integral, we'll add c to the our answer to represent the possibility that there's many of them. All right, now here is an applet that shows you geometrically why this is true. All right, over here on this GeoGebra link, I'm going to graph the derivative of x cubed. X cubed is this curve right here. You can see there's the equation right there, x cubed over 3. So this triangle over here, that's your derivative. So the slope of that line right there, the hypotenuse of that triangle, its slope is being graphed right up here. So for example, at this position right here, okay, the slope was 4. So at 2, the slope is equal to 4. So as I drag this around, it's going to graph the derivative. So you can see that that graphs a parabola, And in fact, that's the graph x squared. So 1/3 x cubed, or x cubed over 3, has a derivative that is x squared. Now, if I take that cubic graph and I just slide it up 2, and I do the same thing, I'm going to drag this and graph it. It's graphing the derivative now of x cubed over 3 plus 2. But you notice it's the same. Right? If I took that integral and I slid it down to around -1, and I did the same thing, graphed its derivative, they all three have the same derivative. That's why we add the constant of integration when we're graphing an integral that does not have an upper or lower bound, because there would be an infinite number of them, and we have to have a way of representing that. That's what the constant of integration does. So we're going to use this working backwards strategy to evaluate these various integrals. So here's our integral. It's an indefinite integral, so we'll be adding c at the end of our answer. So we want to think to ourselves, what function could possibly have 3x plus 2 to the 4th as its derivative? Well, in these first few problems, I've given you a hint. All right, the hint is right here. Well, this function would have, if I did the derivative of that, I would subtract 1 from the 5, all right, and it would end up to be 4. All right, so if I put that function in here, 3x plus 2 to the 5th. Okay, if I did the derivative of that, okay, that 5 is going to come out front, and that would become a 4. All right, so we've got 3x plus 2 to the 5th, so we're going to have to use the chain rule to do the derivative of this. So the 5 comes out front. I rewrite 3x plus 2 times, now I do the derivative of 3x plus 2, which is 3. So the derivative of this is equal to 15, 3x plus 2, and that would be the 4th. All right, but I want it to be 3x plus 2, not 15 plus 3x plus 2. So if I took this original here and I put it over 15, now when I do its derivative, okay, the 15s will cancel and I'll end up with my integrand. So if this had started off like this, when I do the derivative of that, okay, so again, this is the same as 1/15th, so we don't have to use the quotient rule. All right, so that's a 1/15th, and then I'm just going to use my product rule, which is going to be 5 over 3 plus 2 times the derivative of that, which is 3. So I end up with 15 over 15. Whoops, I forgot the 4 again. And then 3x plus 2 to the 4th, and then those 15s cancel. So this would be our antiderivative, or the integral to this, and I would express my answer like the following. 1/15th times 3x plus 2 to the 5th plus c. And that's my indefinite integral for number A, or letter A. All right, I'm looking for, I'm going to use the backward strategy. I'm thinking of a function that whose derivative would be 2x cubed plus 3x squared. So I want to have a function that when I do the derivative, I end up with the integrand 2x cubed plus 3x squared. That's the derivative. Now when I do the antiderivative of that, I want it to take me back to where I started. Okay, so again, I give you a hint. All right, this function right here, if I did the derivative of x to the fourth plus 2x cubed, okay, if we do the derivative of it. So I'm going to do the derivative of that. So the 4 comes out front, subtract 1 from the exponent. The 3 comes out in front and makes that 6, subtract 1 from the exponent. All right, so I've got, it looks like that works, and this one works. All right, so I've got to think, what am I going to do? What would I do to this to transform it into what I want? Which is 2x cubed plus 3 plus 3x squared. Well, if I took the top, if I took that and I divided it by 2, it would make that a 2. And if I took that and divided by 2, it would make that a 3. So my integral, or my antiderivative, remember they're the same thing, is going to be x to the fourth plus 2x cubed divided by 2. And there's my integral. Plus c. So find the antiderivative, or integrate 1 over the square root of 5x minus 1. So again, we think to ourselves, what function could possibly have this as its derivative? Okay, we're looking for a function whose derivative is equal to the integrand. Again, you're given a hint. So it suggests take that and rewrite it, or find its derivative. So I did that over here on the left. All right, so I've got 1 half comes out front using the chain rule, 5x minus 1. Subtract 1 from 1 half, that gives us negative 1 half, times the derivative of whatever's in my parentheses there, which is going to be 5. Right? So this ends up being 5 halves to the negative 1 half, and I can rewrite that as 5 halves, and then this would be over the square root of x minus 1, because it's a negative exponent, so it moves down to the denominator. All right, now I want the result that I'm looking for is, instead of this, I want it to look like 1 over root 5x minus 1. So what I got to do is figure out how could I get rid of the 5/2, so then I would just have 1 over that root. Well, if I took the original and I put a 2/5 in front of it, that would take care of that 5/2. So that gives me my antiderivative. Okay, so I would write that as 2/5 square root 5x minus 1 plus my constant of integration. So by working backwards, many integrals can be evaluated by using the tables that you had for your derivatives. What's different is you're going to read your table, that should say from right to left instead of left to right. So when you were learning how to do derivatives, we worked that way. Now we're going to work the other way. Right, so for example, if we take the first problem here, it says find the antiderivative capital F. All right, so just some notation. Capital F, okay, that's the same as writing the integral. So that's the same as saying, what's the integral of 5? Well, this is telling me if that's my integrand, okay, there's my whoops. There's my integrand, there it is. So that's got to be my antiderivative or my integral. So this is simply going to be 5x plus some constant. All right, number 2. We want to find capital F, which is the same as the integrand of x to the 8th dx. Okay, so now I'm thinking, okay, I got a power. All right, so I'm going to add 1 to that power and divide by the new exponent. And there's my integral. Okay, number 3, integrate 1 over x squared dx. Okay, so I'm going to rewrite this as the integral of x to the negative 2 dx. And then I'm thinking, what function would have a derivative whose derivative would possibly be x to the negative 2? So we can use we know our power rule here. So I'm going to add 1 to my exponent. That would make it negative 1 over that new exponent plus some constant. All right? And I would write that in its final form. That fraction is going to be negative. The x has a negative exponent, so it moves to the bottom. That would just be x to the 1st plus some constant c. All right, integrate the function e to the 3x. So I think to myself, what function would have e to the 3x as its derivative? Well, over here is our rule for e to the x, okay? In this case, it's e to the 3x. So if you remember when you take the derivative of an e, so if I had e to the 4x, okay, e is its own derivative. So this would be e to the 4x times the derivative of the exponent, which is 4. So that would be derivative of e to the 4x. All right, so I'm thinking what function would have e to the 3x as its derivative? Well, e's are their own derivative. So I know I'm going to start with e to the 3x. If I did the derivative of that, I would get e to the 3x times 3. That would be 3e to the 3x. But I don't want that. I want it to be just e to the 3x. So what I need is some way to get rid of that 3 that's out front. So I would do that by dividing my original by 3. Okay, so if this had a 3 out front, then when I did the derivative, it would just be e to the 3x. So my antiderivative here, or integral, is going to be e to the 3x over 3, or 1/3, plus a constant. All right, now I'm thinking what integral would have what function would have a derivative whose value is e to the negative 2x. Well, I know e's are their own derivative. So I'm going to start with e to the negative 2x. Now, if I did the derivative of that, it's its own derivative. And then that's going to be multiplied by the derivative of that exponent, which is negative 2. So this would be negative 2e to the negative 2x. Now, I don't want that. I want just e to the negative 2x. So I've got to think, what would I do to this original so that when I'm done, that negative 2 would get canceled out? So if I had negative 1/2 in front of this, now when I do the derivative, I'd have a negative 1/2 in front, and those would cancel out, leaving me with e to the negative 2x. So my indefinite integral for this would be negative 1/2 e to the negative 2x plus some constant. All right. The antiderivative of cosine we know is sine. So right here, it's telling me that my antiderivative is going to end up being sine. So if I take the derivative of sine, okay, the derivative of sine is cosine, 1/2 x times the derivative of the argument here. The derivative of 1/2 x is 1/2. So that derivative would be 1/2 cosine 1/2 x. Well, it's almost what we want. Okay? We want cosine 1/2 x. There it is. But then there's this 1/2 out front. So if I would take this original antiderivative here and put a 2 in front, then when I do the integral, the 2 would cancel and I'd be left with what I want. So my antiderivative, or my integral, my indefinite integral, is going to be 2 sine 1/2 x plus c. And there's your lesson on how to evaluate indefinite integrals by working backwards. Now, in the upcoming lessons, we're going to learn just rules that we can follow that we recognize a function and we can follow a rule that gives us our integral. All right, have a good day, and I'll see you next time.